This is Lab 5, Magnetic Molasses by iishim Oberoi. The purpose of this lab is to understand how Faraday and Lenz's laws affect real life, specifically how magnets falling through tubes are affected, and the takeaway is to understand how basic real magnets interact with their surroundings. The physics principles in this lab are Faraday's law, Biot-Savart law, Ohm's law, and magnetic force on a loop. The main result was that the magnet was slowed its fall when it was passing through the foiled tube, regardless of which pole was facing up. For our model, we're using a simple magnet with a north-south pole and a tube. Now we're assuming that the tube and the system is the magnet, or the tube and the magnet are the system, and the surroundings is everything else, and air resistant and friction from the tube is negligible. For the actual procedure of the experiment, first we use the magnetometer app to find the north pole of the magnet, and mark that. Then we set up our camera to record the entire tube and film the magnet dropping through it. We repeated that 5 times. And then we found the timestamps of the magnet when it entered and exited, and calculated the average fall time through each trial. Here is the data showing those 5 trials, and the average time was about 1.704 seconds. And the values on the right are just the length of the tube, the width of the aluminum inner radius, and the total radius. MU calculated from lab 3, mass of the magnet, and again the average time. So we can't use a ferrous tube in this experiment because ferrous metal in an external magnetic field becomes magnetized and has a temporary magnetic field which attracts the magnet. So in this case, our magnet would not fall through the tube but instead stick to the side of it. In the tube, the magnet experiences an opposing magnetic force which slows its fall to a constant velocity. In free space, there's only gravity, so it would just accelerate until it hits the ground. Here's my glow script code. Here we're just setting values and constants. Then we're setting the basic mass and MU for the bar magnet. Then we're actually creating the magnetic field of the bar magnet and calculating the magnetic flux. Then we are, what are we doing here? We're getting the gravity of the magnetic field and the magnetic force on the tube from the magnet. Then we're calculating the the magnetic field induced by the dipole on the rings, and then just plotting that all and calculating Fnet. Here's the simulated visualization of the bar magnet falling through the tube and the graph of its velocity versus time. So the red and blue colors indicate current flowing in opposite directions. Which color corresponds to the clockwise and counterclockwise current? How do I know? I said the blue current on top is counterclockwise and red current on bottom is clockwise, and I said I know this because Lenz's law says that the opposing force has an opposing current direction. So the opposing magnetic field is going up, which means that has a counterclockwise current in the tube, so the bottom one must be clockwise. What happens to the dynamics of the system when you flip the magnet around? The same exact thing would happen. It would fall really slowly, but it's just the direction the current is flipped. How does the total in-time tube of your real-world system compare to your simulation? The real-world time is longer. That's probably because the computation model doesn't account for friction from air or the sidewalls of the tube. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The force magnetic from the tube takes a second to oppose the force of gravity. You can tell because it dips down, and then the velocity slows back down. And then, of course, when it starts to exit the tube, the magnetic force kind of gives out, so gravity takes back over. My source error for the experiment are friction from the inside of the tube rubbing against the magnet as it fell, air resistance, and timing inaccuracies. If the resistivity of the conductor was reduced to 0, how would the dynamics of the falling magnet change? If the resistivity were 0 in the tube acts like a circuit, so its current would be much higher, which means the opposing magnetic force would be greater, so it would be a slower fall. And if there was holes or slots cut into the tube, how would this affect your model? Yes, it would affect my model if the circuit is open. So if there was holes or slits in the tube, there would be no flowing current and thus no opposing magnetic force. And then it would just fall. The magnet would fall like it was in free fall. No opposing magnetic force to slow it down.